Hello and welcome back. So today's video is about how you can do a simple coding in the mechanical APDL Ansys language for a truss structure like this. So it's a simple truss structure. You have a fixed joint or a fixed support here and a roller support on the other end. You have two vertical loads. Since the fixed support is angled or oriented this way, you'll think that there are some changes in the boundary conditions, but since it is fixed, you don't have any movement, so the orientation is not an issue. But if it was a roller support, then you'll have to model it separately or differently. So to start with, the first two lines, this finish is to stop whatever the already existing codes on the mechanical APDL platform, and this clear will clear everything. And then you'll have to type in prep 27. In this case, all the elements or all the members of the truss are of equal length. So we type in ET, which means element type. We have only one element type, and then that's link 180. This is the element type that is needed to model truss elements. So from FEA theory, you know that truss elements are basic elements that only have displacements in the axial direction. So we are going to use the link 180 element that corresponds to the truss element. So section type, we have only one section type since the cross-sectional areas are equal. Section type is link. Section data. So when you use section data with only one comma, you're going to input the cross-sectional area. So here the cross-sectional area of the members are 10 millimeters. So I've calculated the area using 5d squared over 4, and that corresponds to this value. Then we are defining the material properties. MP, EX means the Young's modulus. 1 is the first material, so 210 GPa, that's 210 into 10 to the power 9 pascals. And then again, MP PRXY is the Poisson's ratio symbol, so 1, 0.3. And then we are going to create the nodes here. So as you can see here, the nodes are numbered here 1, 2, 3, 4, and 5. So we have to give the dimensions. So n,1 is n corresponds to node. 1 means the first node, so it's at 0, 0, 0 origin. Similarly, the second node is at this length, which is 2 meters. All the members are of equal length of 2 meters. So here 2, 0, 0, node 3 at 4, and here it's 1, and the height is 2 into sine 60. That's 1.73. So we have 5 nodes. Then for elements, you just have to set which nodes you are connecting. So initially for the first element, I'm connecting nodes 1 and 2. So E 1, 2. Similarly 2, 3, 1, 4, and likewise. So you have 7 elements. So for boundary conditions, you know that node 1 is fixed. So you can say D. D means for displacement. 1 is node 1. All means you are constraining all degrees of freedom into a magnitude of 0. Similarly, D3 is a roller support. So you are only constraining vertical displacements, so uy is 0. Similarly, you have forces on nodes 4 and 5, F4 and 5. The direction is vertical downwards, so Fy, you have minus 6,000 and minus 12,000. So once you have done applying the boundary conditions and loads, you can type in this command solve and finally solve. And now we are going to execute this code in APDL. So the easiest way is just copy the code and open up APDL, and then write, and here you can paste it here and press enter. Here it will ask you for it will ask you if it's needed to clear the whole existing commands. So press yes. The solution is done. So to view the results, you can go to general processor. You can go to plot results if you need to plot the shapes, deformed shapes. And you can also go to contour plot and nodal solution or whatever the elemental solution if you need. Degree of freedoms. So this is the magnitude of displacements. Similarly, if you want to list the results, you can go to list results, nodal solution. If you want the displacements, you can check it here. And if you want the stresses, you can go to here and you'll get the stresses here, elemental stresses. Also, if you need to calculate the solutions, so you can go to reaction solutions and just you can select all items and you'll see the reactions here. And then you know from FEA theory that we have elements that are oriented in different orientations. So if we need to find the loads in this orientation in the local coordinate system, then what you have to do is go to element solution. And when you go down, you have something called line element results. So here the element results, then you can get the elemental loads. So here you can see the elemental force and the corresponding stress. So yeah, that's one of the basic APDL codes and examples. So you can do this from the GUI itself, but this is one of the easiest ways. So that you can easily make changes.